Thermodynamics is the study of energy conversion between heat and mechanical work, and subsequently the macroscopic variables such temperature A volumia and pressure. In this module we will discuss the first law of thermodynamics. The first law of thermodynamics can be stated as, the total energy in a system remains constant, although it may be converted from one form to another. It is a form of conservation of energy. For example, when we eat food we convert it to a form of work, heat, or store it in our bodies and use it later. Or when the energy from the sun, the plants can use it for growth and production. The plant can then be consumed by other animals and so on. Basically, the energy from one type of media is just converted from one form to the other and the total energy of the system remains constant. This is the first law of thermodynamics. Mathematical expression of the first law of thermodynamics is shown here in equation 1. Where delta U is the change in internal energy, Q is heat, and W is work done or on the system. Internal energy refers to the kinetic energy of the particles inside a chamber. Heat Q is introduced to the system where it contains an ideal gas. This expands the volume of the gas, pushing the piston upward with work W. The internal energy U changes from state 1 to state 2 and it is expressed as equation 1. The internal energy is the sum of the kinetic energy and potential energy of the particles. Consider the work W. Note that work is given as equation 2. And the pressure and force relation is given as shown in equation 3. Rewriting equation 2 with the condition in equation 3, we get a modified expression for work in terms of pressure and volume. This term here is equal to the volume of the changed length or the amount of volume increased. So we can write it to equation 4. This is assumed at a condition that the pressure remains the same. Here we have a pressure volume diagram at different conditions. The area underneath the curve is the amount of work done. Isochoric process is when the volume is constant. Here we can have the pressure changed at constant volume like with gas tanks for cooking. The area is 0 so there is no work done. An example for this would be the gas tanks where the volume is maintained by the metal tank while the amount pressure is changed as the gas is released from the tank. Here we have an isobaric process and this is when the pressure is constant. Here we have the volume changed at constant pressure and the work is given by the area colored blue. An example for this is a piston engine. If both pressure and volume changes, we have the work done shown by the highlighted blue color. Here we have the sign rule for work and heat. For condition A, the piston is pushed upward by an amount of work which increases the volume. The sign for the work is designated as positive when the volume is increased. At condition B, the piston is pushed downward by a certain amount of work. The decrease in volume signifies that the sign for work is negative. Here we have the sign convention for the heat Q at condition C. The heat enters the piston system which increases the temperature. When heat is added, the heat is assigned a positive sign. At condition D, the heat leaves the system and the temperature decreases. When heat leaves the system, it is assigned a negative sign. As mentioned earlier, the internal energy delta U is the sum of the kinetic energy and potential energy of the particles inside the system. For an isolated system, the energy as shown by the square enclosure shown in the figure, the internal energy is equal to 0 or the energy is conserved and it just simply transforms from one state to another. For this case, the heat is transformed to work pushing the piston and vice versa. So when the internal energy is 0 shown in equation 5, we see that the heat is equal to work in magnitude but opposite in sign as shown here. Let us look at the mathematical equations for thermodynamic processes. Recall, an isochoric process is where heat is introduced or leaves the system by the volume remaining constant. So, if the volume is constant, then initial volume is equal to the final volume, so work is equal to 0 for an isochoric process. The first law of thermodynamics can be rewritten as shown in equation 6. The change in internal energy is equal to the heat, and this is an isochoric process. For an isobaric process where the pressure is constant but the volume changes, the work is given in equation 4. Substituting this to the first law of thermodynamics, the change in internal energy is given as the sum of the heat minus the work shown in equation 7. This is the first law of thermodynamic formulation for an isobaric process. Here we have an adiabatic process where no heat is gained or lost by the system, or in other words, heat is equal to 0. The work is given as shown in equation 4. We see that the work is equal to the change of pressure A and volume. Later we will discuss the details further, the nature of work at these processes. Continuing, we see that the first law is reduced to equation 8 for an adiabatic process where no heat is gained or lost. For an isothermal process where the temperature remains constant as it expands or contracts, the internal energy delta U depends only on the temperature. So, its internal energy is 0 and the heat Q is equal to the work output. The first law is then reduced to equation 9 where heat is equal to work in magnitude but opposite in sign. The work for an isothermal process is equal to the number of moles times the gas constant R times the inverse a logarithmic function of the ratio of the volume as shown in equation 10. These are the equations for an isothermal process. Here we have an example of a heat engine undergoing a Solche shown by its pressure volume diagram. Calculate the net work output of a heat engine following path of the. The first approach is to measure the work by each process. The total work done is the sum of each process. So work total is given as the sum of work done by process AB, process BC, process CD, and process DA. For the work done in an isochoric process or constant volume, which are work BC and work DA, they are equal to 0. The work total is simplified to the sum of work at process AB plus the work CD. Note that the work is the change in pressure and change in volume based on the figure, so we use equation 8. Substituting the values based on the graph, we get that the total energy for the cycle of the heat engine is 4.5 joule. Here we apply a second approach. Here we calculate the total work using the area underneath the curve. Here the total work is the area inside the cycle highlighted in blue. We deconstruct this into familiar shapes. We have a rectangle with a half triangle at the bottom and top. The half triangle bottom and the half triangle at the top are equal in area. So, they cancel each other and we can move the top triangle to the bottom, forming a complete rectangle. Measuring the dimensions, we have the length of 1.5 pascals and the width of a 3 meter cube. So, the total work given in the equation here shows that it is 4.5 joules. Both approaches show the same value, which shows you can measure work using the area under the curve or inside the cycle. Earlier, we showed you the pressure versus volume diagram for an isochoric process and isobaric process where the area under the curve is the work done by the system. Here we will show you the different pressure volume diagram for the different systems using ideal gas isotherms at different temperatures. First we have the isochoric process as highlighted by the red arrow. We see that there is a drop in its temperature as it drops in pressure at constant volume from its initial position A with initial temperature top. Here we have the pressure volume diagram for an isobaric process. We see that there is an increase in temperature as it moves to a larger volume at this position. Here we have the pressure volume diagram for an adiabatic process where there is no heat gained or lost by the system. We see that as it decreases in pressure and increase in volume, the temperature T2 at this new position is less than T. Here we have the pressure volume diagram for an isothermal process. We see that as it decreases in pressure and increases in volume, the temperature remains the same at this new position. An example for this type of process is the melting of ice. A at this position with temperature T3 is equal to Ta. Looking at the relationship of the molar heat capacities at constant volume and constant pressure. In an isochoric process we have the condition where heat is introduced or leaves the system but the volume remains the same. The first law of thermodynamics is given in equation 6. Note that the heat Q is equal to the number of moles times the molar heat capacity at constant volume times the change in temperature. So, the first law of thermodynamics is rewritten as shown in equation 11 for an isochoric process. For an isobaric process, the heat equation is given as the number of moles times the molar heat capacity at constant pressure times the change in temperature shown in equation 12. We recall that the work for an isobaric process is given in equation 4 and we recall that the ideal gas equation shown here. Equating these equations we get the work done for an isobaric process which is equal to the number of moles, times the gas constant R times the change in temperature shown in equation 13. Here we derive the relationship between the molar heat capacities at constant volume and constant pressure. Here we have the equations for the internal energy for an isochoric process or equation 11, the heat for an isobaric process or equation 12, and the work equation for an isobaric process or equation 13. Substituting these equations to equation 1 we get that the molar heat capacity at constant volume is equal to molar heat capacity at constant pressure minus the gas constant shown in equation 14. This equation shows the relationship of molar heat capacities at constant volume and constant pressure. Here we have the molar heat capacities for monoatomic, diatomic, and polyatomic gases at constant volume or in an isochoric condition. We derive its molar heat capacities at constant pressure using equation 14. Shown here are its counterparts shown in equation 15, equation 16, and equation 17. Here we have the table for molar heat capacities for the different types of gases. The molar heat capacities at constant pressure or isobaric are comparable higher than its molar heat capacities at constant volume equivalents. In an adiabatic process where there is no heat or Q is equal to 0, we have the temperature, volume, and pressure for an ideal gas condition shown here. For an ideal gas where it is initially at temperature and volume 1, it is equal to temperature and volume 2 shown in equation 18. Similarly, the same gas at pressure and volume 1 is equal to pressure and volume at 2 shown in equation 19. Here we see the quantity sigma, which is the ratio of the molar heat capacities shown in equation 20. We recall that the first law of thermodynamics shows in equation 19. If we equate both equations here we get that the work for an adiabatic process is shown in equation 21. Here we have an example. 3 moles of an ideal gas are taken around the cycle ABC shown in the figure. For this gas, It has a molar heat capacity at constant pressure equal to 829.1 Joule per mole Kelvin. Process AC is at constant pressure or isobaric, process CB is adiabatic and process BA is at constant volume or isochoric. The temperature of the gas in the states A, C, and B is Ta equal to 300 Kelvin, Tc is equal to 492 Kelvin, and Tb is equal to 600 Kelvin. Calculate the total work W for the cycle. Here we draw the pressure volume diagram in the figure for the system. The first process is an isobaric process for A to C. Recall work is given by the equation 13. So work for A to C is equal to the number of moles times the gas constant times the change in temperature. Substituting the values, we see that the work A to C is about 4,789 Joule for process A to C, which is an isobaric process. The second process for the cycle is an adiabatic process for the C to B path. We see that the work for C to B is about -6,734 Joule for an adiabatic process. The next process of the cycle is an isochoric process for B to A path. We recall that for an isochoric process there is no change in volume, so there is no work done, so work B to A is equal to 0. The work done by the cycle A, B and C is equal to the -845 Joule. Negative work suggests that work is done onto the system according to the sign convention. Here we have an example. You close off the nozzle of a bicycle tire pump and very slowly depress the plunger so that the air inside is compressed to half of its original volume. Assume the air behaves like an ideal gas. If you do this slowly, the temperature of the air inside the pump never changes. For letter A, is the work done by the air in the pump positive or negative? Letter B, is the heat flow to the air positive or negative? And letter C, what can you say about the relative magnitudes of the heat flow and the work? Shown in the figure below is the pump with a closed valve and the volume is reduced to half. The distances between particles are comparable closer. For letter A, is the work done by the air in the pump positive or negative? Based on the sign convention, when the volume is reduced, the work is assigned a negative sign. For letter B, is the heat flow to the air positive or negative? The system is an example of an isothermal, where the temperature is constant. This suggests that the internal energy is 0. So the first law of thermodynamics is given here. For this condition to be true, the sign of heat must be opposite to the work. Since the work is negative at letter A, then for internal energy to be 0, then heat is negative. For letter C, what can you say about the relative magnitudes of the heat flow and the work? We obtained that for isothermal, the first law is reduced to heat equals the work. This suggests that their magnitude are equal but opposite in direction. Here we have an example. A monatomic ideal gas that is initially at a pressure of 1.5 times 10 to the power of 5 Pascal has a volume of 0.08 meter cube. It is compressed adiabatically to a volume of 0.04 meter cube. What is the final pressure? How much work is done by the gas? What is the ratio of the final temperature of the gas to its initial temperature? And is the gas heated or cooled by its compression? Shown here is the reduction of volume by pump as it presses the particles closer. For letter A, what is the final pressure? Note that for an adiabatic process the pressure-volume relationship is given by equation 19. Rewriting this to solve for the final pressure, we have equation 20. Recall that for the ratio of the molar heat capacities it is given by equation 20. We note that for monoatomic gases we have the molar heat capacities for constant volume and constant pressure. Substituting these to equation 20 and we get that it is 5/3. Substituting the values we have, the final pressure when the volume is reduced is about 4.8 times 10 to the power of 5 pascals. For letter B, much work is done by the gas. Recall for an adiabatic process we have equation 21. Adiabatic process has no heat loss or Q equal to 0. Recall the ideal gas formulation which we rewrite as equation A. We then substitute equation A to equation 12 and note that molar heat capacity for a monatomic gas is the ratio of 3 times the gas constant over 2. We get that work done for an adiabatic process is negative 10,800 joules. For letter C, what is the ratio of the final temperature of the gas to its initial temperature? Is the gas heated or cooled by its compression? Recall for an adiabatic process, the relationship temperature and volume is given in equation 18. Rewriting this we get the ratio of the temperature. Substituting the values we get that the ratio is about 1.59. To answer the question, A, if the gas is heated or cooled by the compression. The ratio is greater than 1 which suggests that the final temperature is higher which we can say that the gas is heated. That is it for now and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and a class section. Thank you for listening and see you next module.